Oh, okay.
Okay, let me just say real quick, if you're on Zoom, please mute your microphones unless you've got something to say, please. Thank you.
Okay, let me move this over here, and I think we are all set to go. Thank you very much, Wayne. Hey, it looks like you guys have a good group. I suppose our group is big, but no one volunteers or anything, or very little. It's like two, you know how it goes. 2 or 3 people do all the work, but it's fun. Okay, thank you very much. My name's Ed Fong. So you guys are in Colorado somewhere?
Oklahoma.
Oklahoma. Okay. Oklahoma, okay, the Midwest. Okay, I figured somewhere over there. So you guys are doing you guys are doing okay. We haven't started our in-house meetings yet. I mean, our Delta virus house, we were doing fine until about 3 or 4 weeks ago, and all of a sudden this Delta thing. And so I don't know how it is over there, but it's they're playing it really safe here. Finally, our mayor here. You know, it's interesting. You guys are all educated hams. It's interesting. Every time they try to do something, ultimately everyone knows what they've got to do, which is you just got to get the shot. There's no buts and ifs about it now. And the mayor now of San Francisco says, okay, the only way we're going to get people to get the shot is, you know, they were saying for teachers, even teachers and public workers, you don't need the shot. Great to have a shot, but you just have to do testing every week. But then you have like 7 days where you can spread the thing. And finally, you know, they finally made it a rule here. If you want to work for the public office, as a teacher at City Hall, you must get the shot. So that's good. I'm a scientist at the university, and we know this stuff pretty well. That's all I can say. Anyway, back to, and it's not politics, it's science. Okay, we're ready to go. So my name is Ed Fong. I teach at UC Santa Cruz, electrical engineering. And right now I've got, I only have 3 courses assigned to me. I teach an RF wireless class that's in communications. That's a fun class. Almost all of them get their ham license by the time they end it, because, you know, we go into like 5G communications and things like that. But we started out pretty basic from AM, FM, ham radio level, and then it gets advanced pretty quick. I teach a antenna class, and then I teach a high-speed optics IO class. So I've been doing that almost 10 years now. So anyway, but today we're going to talk about how you make a single band antenna dual band in a simple, doable manner, right? I mean, obviously, there's a lot of ways to do it. You know what they say, if you got money, you can do anything, which is true. Except convince everyone to get a COVID shot. You've got money, but it's free. Anyway, I've got my own personal campaign. Of course, on campus here, it's we've got the same demand. You don't step on campus unless you have a shot. For a while there, you know, they had you can wear a mask. If you don't have a shot, you wear a mask. It didn't work. That Delta virus is something else. Something else. It just penetrates all over the place. So yeah, now it's like you cannot get on unless you show that you've gotten your shot. Anyway, okay. So what we're going to talk about today is, you know, a lot of you folks have had single band antennas back 20, 30 years ago. So how do you make a dual band that's feasible, high performance, and again, you know, pretty durable to meet all the requirements? And what we're going to talk about today, I've covered, I guess the original article was published in 2003, back in February, so quite a while ago. And it's become a pretty standard because it's in the, this technique I'm showing you today is already in the UHF, VHF Antenna Classics ARRL handbook. And it's also in the compendium, volume 8, volume 3. So it's pretty popular, pretty standard. For sure it works. We've sold probably up to about 35,000 of these now. And the ARRL has at least two of their versions there that they've tested, and yeah, it meets the standards. Unlike, you know, oh well, let me tell you, if you get something published in QST, I have to respect them. They really try to confirm that this, you know, if it's an antenna, if it's a small one, you got to send a sample. if it's a little Arduino, they like you to send a sample, at least have show a video of how it works. They really try to double check things because they don't want to be publishing things that just don't work. So, okay, let's move on here. So here are the articles, some of them here. The right one was the original one we did in QST. The left one was on a roll-up version of it. Oh, by the way, for questions, let's wait until the end. It's too hard on Zoom too. Just write them down and I'll be more than glad to answer. The Zoom, the interruptions are just really, really tough. They break my train of thought too. And then our latest one was 2017. Some FEMA had requested that we do a Triband, which pretty tough. I mean, they came to us at the university and said, is there any way you can make a Triband antenna? We really, a 2 meter, 220, 440, all in one, and they had these interesting requirements of had to be inexpensive because they wanted to fill the trucks up with them. We're talking about thousands. Because I said, what are you guys using now? He says, well, we're using there's a Comet one, and I think Diamond makes a Triband base. Because Triband is not very popular worldwide because it's what Canada, us, and a few other countries use the 220 band. Most people do not have the 220 band as a ham band. So there's not as much incentive for the like Comet and Diamond to go make a Triband because they know it's going to be limited sales. So that's why it's so expensive. It's like $180. So anyway, this antenna, FEMA came to us, you make us one for $50. If it works, no radials, it will save us a lot of troubles because the Comet and Diamond ones have radials. So they have it in their van, they put it together. When you have to put things together, you start missing parts like the radials. So I said, okay, let me try it. And so this one is 5.5 feet tall. I think this prototype is a little taller, but we've got it down to 5.5 feet. 2 meter, 220, 440, no radials. So it's pretty cool. We sell quite a few of these. Oh, by the way, so this is how my group raises funds. There's no obligation. There's no obligation to buy, but if you guys want to buy some of these afterwards, I give you the what's the dealer cost price. So my students kind of help me make these. And we'll go through this. What's surprising is over the years, I've noticed that it is actually a difficult antenna to make right. I mean, in theory, you have halfway here, quarter way there, yeah. But actually to get it all tuned right, I don't let them do that. I let them cut the holes, all the parts and everything. I put together every single one and tune every single one. We do this in class as a class assignment, but I don't have them go into production with it. We would lose money. We got to produce these fast. But yeah, it is my antenna class. We do build the Triband as to show the students how difficult it is to do a Triband. Trying to get all 3 bands resonating and being able to tune it is not that easy. If that easy, a lot of folks would be doing it. Anyway, and then we've had to kind of patent a lot of our later designs. And I wasn't really into patents, not this stuff. I didn't even think it was patentable. To making it, JPole and make it dual band, is patentable? Well, it turns out that when we published the QST article back in 2003, a lot of people thought it was a good idea, little entrepreneurs that started selling them on the internet and even calling it the Ed Fong antenna. And I didn't feel comfortable with that, but it was okay with me. Hey, if they're copying and selling, it must be a pretty decent product. Where I got upset was we started buying the products offline just to see. We didn't find a single one that worked right. They were resonating all over the place. They took our dimensions from the articles. And I say in the article, these are just dimensions for our coax, for our twin lead. It's going to vary a little bit. That's why I tune every single one. In fact, we order the ladder line by we do a 50,000 feet order annually. We use up about 50,000 feet, and we special order that from Seminole Wiring. And it's not stuff you just pick up at a flea market. It's all specially ordered with special dielectrics and conductors, and just so it's optimized. But so after our attorney at UC Santa Cruz said, you got to patent this stuff. I go, really? It's Mike Kaufman. He's a really good guy. He says, yeah, you really do have to. So we've had to patent it. Luckily, at the university, there's minimal charge, but still we have to do it. Okay, so let's go to the antenna. So to make a dual band antenna, we started out with a JPole, and I'll tell you why. I could have started out with a ground plane, but again, by the 1990s, 2000 era, you'll find that ground planes weren't as popular, and I'll tell you why in a moment. And also dipoles were popular. This JPole thing really intrigued me. Well, that's pretty cool the way it works. And also it's very close to the ideal pattern when vertical, and it's end fed. And let me show you why. And I'm sure a lot of you folks use JPoles now as opposed to dipoles. Here's one good reason. Here's the best reason why things have gone to a JPole configuration. You go up to our local tower, which is called Mount Sutro, and you look at the main tower for the city of San Francisco, for the communications, for the utilities, police, and fire. Here it is. You take a picture of it now. I wish I had a picture of it 20, 30 years ago. But look at it. There's not a single antenna here that I can see that uses radios. That means they're all using some type of JPole type configuration. And so why? We'll get into why.
Yeah, but for some reason.
But I hear someone's audio is coming through. I'm glad, oh, they muted, okay. So that's really interesting when you go, I took this picture maybe 3 years ago now. Yeah, there's not a single, in less than 20 years, this tower has switched from ground plane antenna. I don't have a picture of it, but I wish I did. I remember going up there in that hill. Yeah, mostly, it was pretty standard 20, 30 years ago. Ground plane, maybe multiple collinears, so it's taller, but you see radios. You don't see notice there are no radios on any of these antennas. So most use an internal JPole design. And I'll show you in a while, you don't need a lightning arrestor. Some people might put one on. So if you guys are using a JPole design and you happen to go and spend $50 on a lightning arrestor, you can remove it. All it's doing is introducing some loss and some mismatch, because it's a DC shorted design. You can't beat that. At DC, it's a short. So when you put your ohm meter across it, it's 0 ohms, and it's constantly discharging. A ground plane is an open circuit at DC, or dipole. Well, I'll show you here. Do I have a dipole? Here's a dipole antenna. Right, dipole antenna is here's the, let's call it the radiating element, and here's the shield element here, and then there's an insulator there. And so when you ohm this across, it's an open circuit. So of course, if there's a lightning storm close by, it will induce just by, it doesn't have to resonate, just by the transformer effect. When you got a 1,000,000 volt or 10 million volt lightning strike over here, it will induce. And all it has to really do is induce 30, 40 volts. Your protection is probably 30, 40 volts at the most. I mean, you can't protect it forever, because if you did, you wouldn't get sensitivity, performance wise. So you need a lightning arrestor. So that, these lightning arrestors that you get at about 30, 40 volts, they short, and they only short temporarily. But if you see in a JPole design, let's see if I have one here. I'll just go through real quick. See in a JPole design, I'll go over this in detail. It's a short circuit. It's a DC short circuit right at the bottom. You can't beat that. It's always discharging this element. I mean, theoretically, you shouldn't induce on anything in here unless you get a direct strike and everything blows up. So you really don't need a lightning arrest. It's the ideal in antenna. It's a DC short, but then you ask, how does it work? Well, no, at 145 megahertz or 146 megahertz, 445, you make it resonate. When it resonates, it goes up. It's just like any tuned circuit, right? If you have an LC circuit, it's a DC short with the inductor, but at the resonance, it's a high impedance. So that's the same principle. Let's go back here. Yeah, so there's the dipole. And if you could put the transmitter right here, you wouldn't need the mass, you wouldn't need the coax, great. But in truth, you can't do that. You always have to lead in a piece of coax. And if you lead in a piece of coax, you need to hold it up with something. And then you need this arm going out. Well, this arm going out, it creates, I'm just trying to explain why this is not an optimum antenna to start your projects with. You mechanical engineers out there, there's a torque point here, right? The longer this arm goes out, the better off you are, because it's away from this pole, which acts as a reflector. But the longer this goes out, the more torque is going to be created at that point. And if you were to even solder this with regular solder, you would have to weld it. If this is long enough over the years, when this wind blows, and as you guys know, solder is really for an electrical connection, not for a mechanical. I mean, it'll do a little bit if you don't put any stress on it, like surface mount devices, but not to think that you can hold this solid. If if there wasn't a torque on it, you probably obviously do, like your plumbing in your house. But if this is going to blow in the wind in the winter and all this, and the further this goes out, it's R cross F for you mechanical engineers that puts that force, the greater that force becomes. Like, give an example. Here, hang on. Let me think of it. Here's a good example. Here, I'll give you a quick example of why an antenna like this just doesn't last. Here's a piece of PVC pipe. I can hold it up vertically easily with one hand because the weight is vertical. But to think I can hold that horizontally, that's impossible, right? There's torque on it. And to think I can hold this up for 20, 30 years with wind, it falls apart. We know this because antennas used to be made that way. So you can't extend this very far out to a point where this doesn't act as a reflector. I mean, it's got to be many, many wavelengths before it doesn't see this as a reflector. So that doesn't hold up. Although, so in principle, if you can put a 30-watt transmitter right in there and get power in it, great, but you can't. So that's why we'll go to the JPole, why we like that. So I was first introduced to JPole 1990s, mid 90s. And when I started testing it out, I found, hey, this thing actually works pretty well. Now, so you say, well, what's the disadvantage of it? I think the disadvantage is minor at VHF. It's hard to implement a JPole at 220 meters. The reason why is, we'll show you in a while. Well, I'll show you right now. It's a half wave dipole and with another quarter wave matching stub. That makes it pretty tall, 3/4 of a wavelength. So while a ground plane is only 1/4 of a wavelength, but it has radials. And I still think the trade-off, obviously, it's much better just have vertical 3/4 of a wave. The reason why is you see that at towers. Again, at VHF, UHF, that's not bad. In VHF, if you start having multiple elements, it starts getting tall. But clearly at UHF, at only 6 inches per quarter wave, oh, you can make gain antennas with this in a couple of feet. That's it. So back here. So that's why I kind of like it. Plus, it gives about 1.5 dB, 1.6 dB of gain over a ground plane. And I'll explain that in a while, why it does that. It's very simple. I mean, you can do all the math, but I'm not a math guy. I like to do it intuitively, explain things, and then go do the math. I find that in my life, I tend to remember it a lot more. But so I'm not going to introduce all the math of why that happens, but we'll explain it intuitively in a while, why a JPole is about 1.5 to 1.6 dB better than a ground plane. So anyway, so I was introduced to this JPole, but by 2000 or so, we have swap meets like you guys have. By 2000, 1990, started getting all these dual band handy talkies, dual band mobiles, and hams love to experiment with their own antennas because they figured we can save money. So people started asking it during swap meet weekends, hey, is there any way to make my single band antenna into a dual band? And what they found was, hey, it resonates. My JPole or whatever they're using, it doesn't blow up when I measure the SWR at UHF. It's a VHF antenna, but it seems to work. Not great, but it seems to work. It does, because if you're an antenna designer, you can explain that portion pretty easily. Most antennas, virtually all antennas, I think, but despite some exceptions, will always resonate at odd harmonics. In other words, if you make 100 megahertz antenna, you will see the SWR dip at 300, 500, 700, and etc. And this is the same case for a 2-meter antenna. And there's no accident that the FCC did this, third harmonics. VHF, 145 multiplied by 3, and you basically fall in the UHF band. It may not be exactly where you want it, but close enough, at least where your radio won't blow up. You put a SWR meter with, it's not great, but it's 1.5 to 1, 1.7 to 1, usable, perfectly usable. But what people found was, yeah, it might be usable from an SWR point of view, but not from a performance point of view. They, without even instruments, they could tell, not performing very well. Well, if you quantify this, simulate it on like EasyNet or ADS, that's correct. You lose about 6 to 8 dBs, and this is why. I'll show you here. Here's an easy, did we do this one on Easy Neck? Yeah, we did this one on Easy Neck. Reason why is you guys have access to that software. You know, Jim Llewellyn has this software that's free now. So if you do this in free space, just as a good reference in free space. So in reality, you know, this is the sky, this is the earth, and this is sea level right here, sea level. And typically you would stand right there, and then your other person or measurement will be here, you know, miles away or yards away or whatever it is. So if you map this pattern, what happens is a vertical dipole, half wave. So you're probably familiar with this. It'll look like a figure 8 pattern. So from looking up from the sky here, it'll cover 360 degrees. And it's just really ideal, the dipole, because it creates kind of a null here. And you want to know here, you're close by. You don't want it in the sky. You want all the energy to go out in the horizon. So it's not bad. A good vertical dipole, if you can implement it, is really quite a good antenna. Except that when you go to the third harmonic, although the third harmonic is a good match, its pattern looks like this. We call it this 4-leaf clover effect. And that's not what you want, because remember, this is the sky. And it turns out that, you know, 4 to 6 dB, about 75% of the energy is in here. 25% of your energy is left here. Usable energy. So all of a sudden your 4-watt handy talkie looks like a 1-watt handy talkie. 4 watts is bad enough on a handy talkie. You don't need to go lose another 75%. So aside from an emergency hitting a repeater, you're probably okay. But it is 1/4 the power. You want to go the other way, right? You want to increase gain, not decrease gain. So we quickly notice that just by simulation. So the question is, could you produce a new design or modifying a JPole design that everyone had and get rid of this 6 to 8 dB loss? And there's probably a lot of ways of doing it, but I think the main criteria for hams is, but it had to be simple, reproducible, no radios. You couldn't add radios. So it had to be practical. No inductors, no fancy inductors that you got to buy, costing $10 to $20. That's just would be not practical. Now, the other thing I've noticed is whenever you modify an antenna, you know, at VHF, UHF, or if you take one apart, take a diamond, whatever manufacturer apart, tram. This is the pattern we notice, and you know, I kind of do this as a hobby profession. You kind of get paid at the university to just look into things, right? Especially you have students look into things. Hey, go look into this. Tell me what it is. So that's the great thing. You're curious. You don't have to do all the work. The students just love this practical work. They hate, believe it or not, most of them hate. I don't know how many engineers are listening here. Most of them don't go into engineering because they love Fourier transforms, discrete Fourier transforms, Maxwell's equations. If you're into that, most of these guys are physics mathematicians. Engineers, we like to build things, right? We like to make things and see them work and make measurements. We're typical engineers don't sit under a tree, drinking wine, eating French bread and thinking, oh, what can I think about this? Number one, there's not very many jobs like that. Most jobs say, hey, you're an engineer, you come on in here, we got a project, you got to build this radio or building or whatever, and then we pay you once it's done. There's not very few jobs around there here that will pay you to drink wine, eat French bread, and just look at the stars and come up with ideas. And that doesn't happen. So that's what I find most engineers, they don't care for the math. That's not their main thing. It's a tool. Math is a tool. They like to build things. So anyway, what's interesting is we found that antennas, when my students start taking them apart, and again, they love this, they try to actually teach them reverse engineering. Antennas at VHF, UHF, if you see a capacitor for matching, not a good antenna. We see some of these copies, they use cheap ceramic capacitors. And we've got good network analyzers in our lab. In fact, I've got one right here, right? I just happen to pull this out, that's why. Well, we're not using MFJs here, we're using Agilent, 5062s, 6 gigahertz analyzers. They're the best that money can buy. So we look at these things and there's no capacitor that works really well at at 450 megahertz. You've got to use other techniques, strip line techniques, transmission line techniques for matching. But I am surprised that you open a Diamond X200. They use capacitors. I mean, that's just, and what's interesting is when we do these tests, again, I got free labor. Our antenna, amazing. I was shocked. And the reason why I knew this is other clubs that we had sold antennas to was trying, I mean, and they're so cheap. We sell them for, $32. So they buy a bunch. The weekend, they do the same thing. They have a little shootout contest. Ed, your antenna works just as well as an X200. And so we start testing that. In fact, we've bought at least 4 or 5 X200s from different batches and things like that. We find, does the antenna work, X200? It works. It works as good as ours does, an actual field test. But you open, so we start reverse engineering. There's too many, I mean, I can't believe they use ceramic caps. It's like a 10 picofarad ceramic cap, and a 22 picofarad one. Are you joking? There's no way. That doesn't even make sense, because you can put that capacitor on a network analyzer. It's got a lot of series resistance, and it's got some inductance associated with it, because it's at 500 megahertz. I mean, you can do this at HF. I mean, you guys have probably played around with traps at HF. I was playing, and they're already tricky. Traps for multi-banding a dipole at HF, making little coils. You got to seal them, make sure you don't get moisture in it. And to think you can do that at 500 megahertz, you're dreaming. You're dreaming. So anyway, back to our thing. So I hope you guys don't use like X200s. The antenna works, but in field tests, no better than ours. No better. I can prove it. I could take pictures of 4 or 5 of them I have here that we've taken apart and looked at. Anyway, okay. So what our goal was to convert a JPole now. We've taken the JPole. We like it. It doesn't need a lightning arrestor. Doesn't have radios. Oh, that was my project. We'll take that. Let's see if we can add UHF to it without having the lobes. So basically, we know that the antenna's matching is not the problem. Again, at VHF, it would also resonate at UHF. And okay, quarter-wave decoupling. Okay, I'll show you how this decoupling stub works. So let's go on to the, okay, so we went to this pattern, and in order for me to explain how we solve this, is really important with antenna designers, is just understanding the basics of a Smith chart. Just for antennas, you don't have to understand it as much. You start designing amplifiers with it. Yeah, there's a lot of things a Smith chart can do, but the main things you have to remember, what the Smith chart shows is that you can start out at 0 ohms. Now this is not DC, AC. So let's get a little stub here, quarter wave stub here in my lab. I have. Find one. Here we go. Here, this happens to be quarter wave stub at UHF, which is about at UHF about 4.5 to 5 inches. Just a piece of coax. But you have to understand what a piece of coax does. It's an open circuit, right? It's an open circuit, but that's DC. The thing I try to get across to my RF graduate students is this. It's amazing that DC and AC are the exact opposite of each other. For example, I say, well, you get a piece of aluminum foil. At DC, that's a conductor, right? That's a conductor, aluminum foil. But at AC or RF, it's a shield. So one's a conductor, but at AC, it stops it. It's an insulator in a sense, if you want to look at it that way. I said, well, what's wood at DC? Well, wood at DC is an insulator, because if you get an ohm meter across it, you don't read anything. What is it at RF? It's a conductor. Of course, it's a conductor. That's how radio waves go through a building, right? So you got to get that in your mind. It's almost direct opposites, and it is confusing. It is confusing. So the Smith chart kind of straightens that out, but to keep that's the basic thing we teach. If you can understand that they're almost opposites of each other. Because if I didn't say that, one would say, here's a piece of coax. If I short this end, just solder short piece of coax, what is it at this end? They go, oh, short. Wrong, it's not a short. You got to understand hang on, I see the audience here. I want to see how many of you guys are like technical background, as a job, EE, technician or something. Show of hands. I can see you guys. No, not that many. You got Leah is one, but no, not many. Okay. So how about raise your hands? I see the audience that you understand what I'm talking about. Most. Okay, some. Okay. So let me explain it. Okay. So that's the thing you got to get in mind. If you short this side, it becomes a short only at DC. If it's an open here, you think it's open here. That's only DC, only DC. And boy, that is a tough one to get across to people a lot because it's not intuitive. What do you mean? You short a piece of wire, it's got to be a short circuit, only at DC. What the Smith chart shows you is if you short something, 0 ohms, right? 0 ohms, you start with 0 ohms. As you move 1/4, the Smith chart represents 1/4 of a wavelength, 180 degrees, 1/2 of a wavelength, 360 degrees. So every time you go 180 degrees, it represents a quarter wavelength. So what the Smith chart says is if I short one end and go a quarter wavelength, and at UHF, it's got to be at a particular frequency. So at 445 megahertz, our UHF, it's about 4.5, 5 inches or so. If you go here, that will read maybe not infinity, but pretty high, right? Thousands of ohms. And vice versa. You say, open circuit? What's an open circuit? How simple can that be? It gets pretty complicated. An open circuit, believe it or not, it will read a short circuit here at a quarter. So a quarter wave for this is about 445 megahertz. That's what it would read. And that you got to get through your thick head. I know it's very counterintuitive if you grow up playing around with little light bulbs and little telegraph sets. All of a sudden you move into RF, it's a different world. So if you have that in mind, then we can move on. Because here is how a JPole works. If you guys have wondered how a JPole works, it works like this, without all the math. So here's a dipole antenna, 2 meters, 37, 38 inches, depending what frequency you want, but it's in that range, 37, 38 inches. Because a quarter wave is like 17, 18, 19 inches. It can depending on where you tune it. So normally in a dipole, so pretend this is like twin lead, you would have center fed it. Right? You would have center fed it. And that's what we did here. When we showed this dipole here, that's a center fed dipole. And again, it works fine if ideally you can set up a transmitter right there with no coax, but you can't in real life. So you want to come as close as possible to this. So the middle of this is 70, 50, 65, 70 ohms or so. You can feed it with a coax, but again, it's not desirable from a mechanical point of view because you'll need a perpendicular piece of coax here, and then you'll need a mass, and it's just not very practical as been shown over the years. And also, what's important is it's going to be an open circuit. You have to break the center. It's going to be a DC open, which means it's going to open itself to lightning, static charge, and all this stuff. Well, here is the JPole. So if the middle is a low impedance, most of your radiation occurs at the end. That's because at the end of a dipole, the voltage is the highest. If the voltage is the highest, the current must be the lowest because it's the same power going throughout. So at the ends, that's a high impedance. It's not infinity. Ideally, on paper it's infinity, but it's in the thousands of ohms. If you put an analyzer in, it's in the thousands of ohms. So the trick is then how do you match it? If you want to end feed something, whether it's 20 meters or whether it's here at VHF and UHF, you need to convert that 50 ohm coax that's driven by your radio, which is 50 ohms. You need to make some type of a transformer that would transform that into high impedance if you want to feed it at that end. Well, back to the quarter wave stub. I just said is a short circuit, like here, you short circuit one end. And if you go a quarter wave, it's infinity. And somewhere you could say, well, if this is infinity or thousands of ohms and that's 0, don't you kind of go across 50? You do. And you say, well, not exactly. You have a little bit of inductance. Yeah, you do. That's why it's not perfect, but it's not bad. it's really not bad. Here's very high impedance, which matches the end of a dipole. That's a short circuit. So it's short circuit here, which is great. DC short. It cannot hold a charge at that point, not for very long, because it's a DC short. And somewhere along that line, at about 1.25 inches, it's about 50 ohms. And we actually did this experimentally. You just play around with it. It's a network analyzer. So here's how your basic JPole works. Let me get a show of hands. How many of you folks use a version of a JPole? Yeah, a lot of you folks. Yeah. I think very few of you now use ground planes. This is just, it's just engineering design. Engineers figure things out over the years. We land man on the moon if you give us enough money, time, right? So this is what they figured out. This is a superior design. But again, the disadvantage, it is pretty tall. You're talking 40, 50, almost 60 inches here, right? 40, 50, yeah, not quite 60 inches. It's pretty tall, as opposed to a ground plane, which is only a quarter wave, which is about 18 or 9 inches tall, but it has radials. And again, you can hold it very easily. So that's where the JPole comes in. It's a nice, neat, clean design. And there's versions of it. I think earlier we saw versions like this. These days, you see these at swap meets, you see it on eBay too. Kind of expensive. I tell people, it works. We built these. I mean, I have one of them. We build these in our lab. Just to demonstrate to them that this principle of a JPole works regardless of whether you make it out of a PVC pipe or copper. And the reason why I wouldn't advise copper is we found that the simple way we make it out of twin lead works just as well. And here, the cost, you've got end caps, you've got a coupler, you've got a T, you've got an elbow, and then you got to weld it or solder it. It's quite elaborate. It doesn't look very nice. It works. It does work. We build them and they do work. The only problem is that they don't work. This version does not work very well at UHF. And where the drawbacks is that the spacing. Remember, this is the quarter wave transmission line. This is a decent transmission line at VHF because VHF is 146 megahertz and a quarter wave is 19 inches. So this transmission line is about 1.5, not a little under 2 inches. Well, that's okay. So this acts as an okay transmission line at VHF because again, quarter wave is about 18 inches and this is only about 1.5, 2 inches. It's acceptable. It's about at the limit. But at UHF, remember at UHF, quarter wave is only 5 or 6 inches. You can't use a quarter wave 5 or 6 inches UHF and think that this is going to act as a good transmission line. Too much of it radiates already. By the time it hops across, that's almost 2 inches. It starts radiating your UHF signal in the wrong polarity. It's horizontal. So we found this does not work very good at UHF. At VHF, it's decent. It's just it's kind of cumbersome to make. So that's one version of it, of the JPole. And then here's another version of the JPole. Now, I want to explain to you why at UHF, it doesn't work very well. Actually, a better, since I mentioned, I think I have a pattern. Here. So here is our version of a dual banding. I'm just going to show you here. Here's the matching section, VHF, that's quarter wave matching. It's about 15 and a quarter plus 1.25 is 16.5 inches. And a lot of folks, I think a lot of you folks know that, but let me review that. You go, wow, 16.5, shouldn't it be about 18, 19 inches? It is, that's true. 18 or 19 inches comes from the formula C is equal to F lambda. The speed of light is equal to frequency times the wavelength. If you work that out, speed of light 3 times 10 to the 8th meters a second or so. Frequency 146 megahertz. You work out lambda, quarter wave, is about 18, 19 inches. Why is it 16.25 for a quarter wave? That's because it's in the twin lead. The twin lead, remember the formula is the speed of light is equal to frequency times wavelength. But the speed of light, or the speed that the wave travels in the twin lead, is obviously slower than the speed of light. That's called the velocity factor. It's how much it slows down the speed of light, about 10–15% or so. So instead of about 18–19 inches, it's about 16.5 in twin lead. So that's why they say the velocity factor of this is 0.8, depending on the manufacturer. But here's how we've mapped the quarter wave. So it's a short circuit here. This is for 2 meters at quarter wave at VHF. Obviously starts out as a short circuit, so the voltage must be 0, current's maximum. Here's your matching 50 ohm point. And then as you go up a quarter wave, the voltage goes up, 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 which means the current goes down, which means the impedance is going higher and higher and higher. That's at VHF, so it kind of looks like this. At UHF, it looks like this. At UHF, a quarter wave ends about here, ends about there. But the reason why this matching stub still works is you go another half wave, right? Another half wave, it dips back down, which is here, and then all of a sudden it goes back up again. So it goes back up. It goes back up to high impedance or high voltage, which is a high impedance. That's why the matching here, this will match both VHF and UHF. What the problem is at UHF, you would like to feed this half wave, you would like to stop it at about 11 to 12 inches, depending on the frequency you're using. But if you kept the antenna like this, what happens at UHF? You would like it to just cut off at about 11, 12 inches, but it continues. If you don't do anything to it, it continues. That's where you get the lobes. You drive the currents here. It would like to have seen 12 inches stop. With it like this, it doesn't stop. The currents will continue. And if it continues, what do you think it happens? It starts pulling the wave up. It pulls the wave up. So that's why you get these lobes. What you would like to do is somehow electrically or make a trap where it cuts off at UHF at about 12 inches. Then you don't get the lobes. But of course, and then at VHF, you want it to continue. So let me go through this again. So here's the JPole you guys use. Here's another version of it. Arrow puts it out. So Arrow knows about this problem 15 years ago. So, yeah, you can't use a 2 meter JPole at UHF. It works better than nothing. Not better than a rubber duck. In fact, a rubber duck works slightly better. But we want to do something about it. Their engineers came up with, and I don't know who came up with this design, but it's pretty clever. They put an extra resonant element there. 6.5 inches, quarter wave. So what you see is, you see two antennas. When you feed it, UHF sees this, right? 6.5 and 19.25. So here's the JPole at UHF. But at VHF, you see this. The whole thing. So yeah, it's about 60 inches. And we have them here. We tested it out. Here. Right here. And does their principle work? It does work. It is an improvement. It's about a 3, oh, even a 4 dB improvement over just the single band JPole at UHF. And the reason why it isn't a complete improvement is this. They have a single feed point. So at VHF, the resonance is this element here with that element there. And at UHF, it's this 19.25 inch element here with the 6.5, with a single feed point. So when you feed a UHF signal, if both VHF and UHF are matched, half the signal goes in here, which is the proper, but still, if it's a good match, let's just assume they're equally matched. The other half still goes into the wrong portion. And to the wrong portion, you lose about 75% of the energy. So you look at it, half of it's going to the correct antenna. The other half, you lose about 75%. So is it a measurable improvement? It is, but it isn't perfect. And then the last slide I have, okay. The last slide I have is a Slim Jim. You hear about the Slim Jim. You can Google Slim Jim and you come up with these designs and all these crazy things. I mean, it's as political as the COVID shot. People say, you know, I do this for a living. So does Larry Seebeck. The Slim Jim does not give you 6 dB of gain. It might compare to a rubber duck or something. It is no different. We've simulated it. We've done tests. You don't go shorting the little tip and voila, 6 dB. No, getting gain is much more complicated than that. It does nothing. I mean, it doesn't do any harm. It's basically a VHF antenna and also UHF losing 6 dB. So don't get fooled by. I'm going to build myself a Slim Jim because this article says I get 6 dB gain. It's basically just a JPole. Just to clarify things. And there I can say this because I am an antenna designer. I do have a PhD in it. I do have some say of what works and what doesn't work. COVID shot, I listen to my colleagues at the university. And the same thing is they listen to me. When they have an antenna problem, they come to me. That's how life works. Right? If you have a heart attack, don't come to me, right? Just because I have a PhD, don't come to me. You go to a heart surgeon, right? I love this story, by the way. I love this story. Here, Leah's laughing. This is the greatest story I've ever heard. I go, well, you never know. Someone could be wrong. And you got to listen to these people with no background in medicine, epidemiology. They might be right. I go, well, you know, the next time you have a heart attack, don't go to the emergency room and go to a homeless person in the street and says, I'm having a heart attack. What do I do? Because just by some remote possibility, they might know more than the heart surgeons and the cardiologists and all that. That's how we see the logic. Okay, anyway, so how do we solve this problem? Could a homeless person have solved this problem? Unlikely, because you gotta be good at, you go to people you should trained and you have to trust their judgment. You know, Dr. Anthony Fauci, he's probably, you know, he knows a lot more than I do about his field. And maybe if he wanted to get a ham license, he would call me, right? He hasn't called me, by the way. By the way, I have met the man. And Tony Fauci's a really nice guy. I met him 30 years ago for lunch at NIH. A long story, but I had lunch. He's a really nice guy. Obviously, tremendous patience, right? Tremendous patience. Anyway, yeah, he's a really cool guy. At 80 years old, I don't know how he goes, but it's amazing at 80 years old. Okay, so here's back to this antenna. So we feed it the same way. That was never a problem, the matching, because at UHF, you add an extra half wave. That's another way of saying another spin around the Smith chart, the impedance stays the same. It matches. The matching is not the problem. So what you got to do is you got to cut it off at about 11 1/4, 12 inches, depending what frequency you want. You want this cut off. Then it works at UHF. Because if you didn't have this little stub here, it will continue and you get those lobes. So what do you put here? Again, back to this really cool concept of a short circuit. You put a piece of coax, short circuit. If you short circuit it and at 4 1/4, 4.5 inches, it's an open circuit only at UHF, not at VHF. I'll explain to you what it does at VHF, fortunately. It's an open circuit. So therefore at UHF, the wave matches here, you drive it, it goes through here, the voltage plots look like this, and it feeds it, it sees a half wave gray. And at VHF, the voltage with this quarter wave stub looks like this, and then it's supposed to see about 36, 37 inches. And you add all that up, I think it's like 37 something here. This is the half wave at VHF. Now, of course, the question becomes, well, what happens to that stub at VHF? Fortunately, not too much. We actually analyzed it. So here's another version of it rolled up. One of my students came up with this idea. He was a backpacker, and so am I. I used to, at least. He says, can you make this thing all rolled up? And then we worked on it, and yeah, that's when we did the other article, the roll-up version of it. It's the same. The theory is the same. It's just that you got to do it just right. Cut the little notches and all the stuff in the right places, and put heat shrinkable tubing, and it holds up really well. So, so here's an important thing. If you add up all the dimensions here with the one that goes into a PVC pipe, as opposed to a roll-up, which doesn't go into a PVC pipe, right? A roll-up looks like this. I have one here. This is my work, right? So this is how this works. if you look at this antenna, here it is. I'm gonna pull it out of the package. I don't know if you can see all this, but here's a little cable going into the stub. There's a little notch here, a little notch there. There's a little RG174 coax, and here's the last 17-inch piece. This goes into this PVC pipe here, which is, thank God, some chemists, again, I don't interfere with other people's field. They figured this out. PVC now, they put enough research into it, will not deteriorate, as you guys probably already know this, in sunlight. The old stuff used to turn brittle, yellow. No, the new stuff does not do that. It's treated. It's the same formula that they make 30-year vinyl windows with, so it's pretty tried and true. It'll go 30, 40 years and it won't break. And it's cheap, right? Really cheap at Lowe's. So you just stick this antenna into the pipe. And here's the end-fed connector, SO239, and voila, you have a good antenna. But what you'll notice is this: if you add up all the dimensions here of the one that goes into the pipe, as opposed to the roll-up, as opposed to the here, as opposed to the roll-up, which is all one piece, this is not designed to go in the pipe. It's just designed to be hung from a tree or a balcony or something. And you add up these dimensions. It's about 2 inches longer. This roll-up is about 2 inches longer than the one that's going to go in the pipe. Why? Because when it goes into the pipe, you slow down the speed of light, and the wavelength is always equal to C is equal to F lambda. In that case, the C, when it goes in the pipe, is about 3 to 4% slower. So in the end, if you add up the dimensions here and you add up the dimensions there, this is about 2 inches longer in the end. So don't be surprised when people buy both. Hey, the two antennas don't even match. How can it work? That's the reason. The roll-up is going to be a little bit longer because it radiates directly into air, not into a PVC pipe. Okay, we're going through this. Oh, and so we tried out a bunch of PVC pipes. You figure, how do you know this PVC pipe is good? We tried a bunch out and we found that the Lowe's one works the best. 23990, it's cheap. Others probably perform okay. We've in a very, very simple way. If you're not sure of the pipe you get works well RF wise, you don't need a bunch of fancy equipment. The fancy equipment you already have at home. It's called a microwave oven. Cut a piece of it. If you put it in there for 5 minutes, you hear sparks, that means it's got conductors in it, some fibers or something. If even it gets warm, that means it's absorbing RF. So that's how you know. And most do not. Most are fine. Most are fine. But that's a good way of testing a material these days. You don't have to have a bunch of sophisticated equipment. If it gets warm in a microwave oven after 5 minutes, you know it's absorbing RF. Okay, so here we actually do the performance test. And sure enough, the 2-meter JPole at UHF, here's a reference point, just a relative thing with a 8591 spectrum analyzer. We did this in a test in a parking lot, clear. But when we use our antenna, the DBJ-1 at UHF, yeah, you certainly do get back about 6 dB of gain. So it works. And we did actual measurements. And these measurements, we had fun doing these. We talked to the National Institute Standards of Technologies. Well, a typical antenna should be tested under 3 conditions: rain, overcast fog, high humidity, and a sunny day, because it will vary. Because again, the velocity factor, right? The speed of light, if it's really damp, the speed of light slows down. And if it's really dry, it speeds up. And yeah, so we took these measurements, and sure enough, it's minus 24.7 dB was a reference. And a rubber duck loses about 6 dB, which is expected. A standard JPole loses about the same. Oh, this is a VHF, I'm sorry, a VHF. So a quarter wave, minus 24 dB, and a JPole is about loses only about -23 under these conditions. So it is better than a ground plane, even in field tests like this. And ours is about the same as a regular JPole. It may be a little bit lower. It may lose like 0.1 dB because of that little stub. But overall, it's very close. And this is out of 5 measurements each time we 5 measurements each at a sunny day, a rainy day, and an overcast day. So this is actually 15 measurements average. And you know, when you do that, it turns out those ideal simulations are pretty good. They turn out to be pretty good. Now at UHF, that was where our problem was. Using a VHF JPole at UHF, an actual fuel measurement had too much losses, about 75%. So let's take a look at this. Same situation. I remember this. We were just in a parking lot reference. Use a quarter wave mobile, -38.8. That was like 50 yards or so. We were doing this test. So that's a reference, -38.8. A rubber duck at UHF doesn't lose too much, a couple of dBs, 2 or 3 dBs. And if you really worked at it, pick different antennas, and it might even be less, but it's about 2 to 3 dBs, a rubber duck at UHF. The standard VHF JPole, this is at UHF now. It loses about 6 or 7 dBs, right? -30, also that's at -45. That clearly loses it. But if you use our JPole and measure it, it's back, -38.8, and it's at -38.9. It does not quite make it because, like I said, this when you say a stub is at infinity, it obviously is not infinity. When you measure it, several thousand ohms, a quarter wave stub, short is, if you measure it and analyze it, you would like infinity, but it isn't. It's in the several thousands. So it's not quite perfect, but boy, it's better than losing that -45. And now it's at -38. That's why 6-7 dBs of gain. That's a lot. You don't even need instruments really to know that the performance. You know, unless it's a strong repeater, you could tell 6 or 7 dB of gain. So here's our lab. This is a picture taken a while back when we did these antennas. But now we still have this. The students still use this. But you know, we use these now. I tell all my students in our RF class and our high-speed IO class, buy one of these nanos. You know, for $60, it's a steal. You can't beat them. Learn how to use it, and for what a ham would need, it is as good as our 80. This is an 8753, which is $80,000 piece of instrument. For what a ham uses for, it's fine. It's absolutely fine. And then I just like you demand a textbook, right? I demand one of these in my RF design class. You don't have one, drop out of the class. You won't pass, because I did homework assignments and everything like that. And of course, we've got the new one I just showed you, the 5062. That's a really nice unit, but you know, in most cases, I don't need it. I mean, it's a really critical, we're tuning something really critically, sure, for paper or something, but to get everything in the ballpark, these are fine. I mean, the only thing it lacks is, you know, it doesn't have quite the dynamic range. Who cares? It doesn't matter that much now, just for playing around. For hams, it's fine. So that's what we use. Okay, here's an interesting. So here's the stub. Here's that quarter wave stub at 445 megahertz, actually right there. See, it's not infinity. It should have been there, but that's really hard to do. It's more like here. At least it's not here, right? It's not 50 ohms. It's way higher. It's several thousand ohms. So it really helps the situation. In the end, you know, you get within 0.1, 0.2 dB of ideal, which is quite an improvement over 6 dB of loss. And the stub is pretty stable. I looked at the stub. I said, well, how stable is that point if I put my hand around and yeah, it's not stable in other places, but right at 445, it's pretty stable. You would like it to be here, but it's there. Helps a lot. Not perfect, but it helps a lot. And then you'd say, well, what does the stub do at 146 megahertz? Well, it's a stub. It looks like a capacitor between the center conductor and the shield. Not ideal. But we look at it at 146. This is the stub. It's not infinity again, but that's how it looks. And then we compared it. You got to compare it to a piece of wire, right? It would have been just normal wire there. And you know, wire kind of looks like that. Seems close enough. Not perfect, but boy, it's quite an improvement, right? It's the overall performance of the antenna is night and day compared to that 6 dB loss we were getting. That's just, to me, everyone notices this. Now, you know, at the 0.1 dB level, you need pretty good instruments to even measure that. So here's how it looks, right? It's about 60 inches tall, but the thing is, all the torque is down here, not horizontal, or you're trying to hold up anything. So it holds up really well. It doesn't look bad. It's white, easy to mount, really easy to mount. In fact, I tell folks, the antenna doesn't know the difference. Just clamp it on to the side of their building or clamp it on with your vent pipe. It works fine, as long as it's in the clear. You don't need some fancy tower. The antenna doesn't know that you're in a fancy tower, except that you're in the clear, right? The important part is get the antenna in the clear. And here's the roll-up version. Here's the antenna, and we also include a 6 feet extension, an RF extension. We have these made. You know, it's got a male BNC and a female, so you can just hook it up like an extension cord. And we sell these for like $5 each if you want. But one of my students said years ago, you know, if you're going to sell these things, buy the stuff by the thousands, like the adapters. So it starts out as a BNC male, and we throw in the adapters to go to SMA male and SMA female for their, like the Baofangs. And then of course we also have the adapter for BNC to PL259. Not everyone needs that, not for handy talkie, but we charge like $250 for that adapter. It's an accessory you want to get. Okay, I think, oh, so if you like this talk, okay, at the end of this talk, any questions at this point? Sure, yeah, turn on your mic.
Yep.
Unmute.
Go ahead. Any questions?
Can you hear me?
Sure, go ahead.
2 questions, Dr. Fong, and God, I love your antennas. I built every
Oh,
one of
good.
them. Have you ever substituted the RG316 in place of the RG174? And would the velocity factor difference have a significant change in resonance?
It will have a change. I don't know what's significant. We do a 250 watt version with RG8X. And you say, why don't we do that? It's a lot harder to build. And if you're doing onesie twosies, yes, that RG174 is more amiable to the twin lead. So our standard one is RG174, which will handle spec'd out at 75 watts. And if you want a special request for a 250 watt version, we built the stub and the lead-in coax with RG8X. But it's a lot harder to, just physically, it's hard,
Okay.
that's why.
I was just under the belief that 316, you know, actually has more capability than the 174.
Okay, what's 316? I'm not familiar with it.
316 is used internal coax in a lot of amplifiers. It's used in oscilloscopes. Very excellent capabilities to it. The velocity factor on it's 0.66.
Okay, same thing, same as RG174 then. No, that's probably expensive.
I may have told you wrong because I was thinking, I may have been thinking 174 when I said 0.66.
Yeah, so I haven't used that. It's probably, it sounds more exotic. 174 we buy in 1,500 feet rolls, relatively inexpensive. And then it doesn't travel very far, right? We're only talking 8 inches. The losses, that's not where we're getting the losses. But yeah, I mean, you can use anything, just compensate for the velocity factor.
Okay, and my second question is, have you done any testing by painting the
Yes.
200 scheduled PVC, and is there any loss factors there?
Hey, you might think we're crazy, but I tell you, when this painting idea come on, there is a master's thesis. You say, master's thesis on painting an antenna? Well, that's how practical hams are. Come on. No, it actually gets pretty complicated. The chemistry involved, the velocity factor, we did measurement. Actually, the student that does this, his main thing was, how do you measure the task that it takes to measure the difference between 2 antennas, one painted, one unpainted, and then testing different paints. So 10 years ago. And what we found, what his conclusion for a ham, long story short, without all the reflection coefficients and anything can get really mathematical, whether it's relevant or not to a ham. I'm a true ham. I mean, I went through all the math and all that stuff. I just like to tinker, and then when I have to analyze something, sure. We found that Krylon spray paint, the stuff you buy at Harvest by Krylon, is very, very good. You can put multiple coats, and it doesn't change the velocity factor of any significance. spray 2 or 3 coats to cover your antenna, you're fine. We didn't find, I mean, yeah, measurable, but irrelevant. I mean, 50 kilohertz here and there, come on, that's irrelevant. That does, and that's like after 3 coats. So you'll find that if you use Krylon spray paint, pretty good. Okay.
Right. And also I've noted that there's, quite a bit of difference these days, it appears, in what's called 300 ohm twin lead.
Oh, of course, there's only one manufacturer in the world that still makes it. Believe it or not, we checked. We even went to China and said, can you make this? Because we could, but we'll have to make a new die. We had a meeting with Steve Lampin, the vice president of Belden, that used to make this stuff. And they said, no, we won't make it. So the only manufacturer of 300 ohm twin lead, actually, I guess they make it to the public. I'm not sure. We have a custom made for us, is Seminole Wiring. That's the only company in the world. Anything else you get is probably surplus. It's the only Seminole Wiring. And you can buy that through HRO. They will order it for you.
Okay.
Where have you seen it? Because I would love to know if anyone still makes that stuff. We looked all over.
Well, I found it at the old Radio Shack. I found
Right.
I found some at Home Depot that was more of a foam fill
Yeah.
insulator, what they call the
All those have different velocity factors. Yeah,
exactly.
There's no good source for that stuff. Surplus, yes, but we use about 50,000 feet of the twin lead per year, about 50,000.
Ed,
So we had to go to Seminole. The good thing about going there, then we told them exactly how to make it up, what characteristics we wanted, because at 50,000 they'll do it until we get exactly what we want.
got a question that how that old style vintage twin lead varies the equation, velocity factor probably.
All over the place.
Yeah.
Not worth it. We found that we'd rather go to Seminole Wiring. You give us 50,000 feet of the same run, right? Then it's pretty consistent. Otherwise, yeah, you're retuning every time you get a new lot in. It varies quite a bit, like from 0.7 to 0.9, yeah, quite a bit.
Yeah.
Okay, any other questions?
Well, I will ask one more because I don't
Sure.
want to dominate your time, but like I said, I love the design. From the DBJ-1 and DBJ-2, the DBJ-2 designed for in coax or in PVC and out. I know that the slot there at the end of the first run where the 174 starts, you remove the opposite side of the twin lead. Is that removing a resonator, or what faculty does that play?
I'm not clear on that. I removed the opposite twin lead.
Well, you look at your drawings between number
okay.
17 and number 18.
Sure, okay.
And you see that one side has the wire missing.
Left. Here. Oh, in the DBJ-1, that's about 8 inches, and it goes to the SL239 connector.
Okay.
And of course, in the roll-up, we have to do a BNC.
Okay. Now,
That's the only difference.
The other aspect is I have substituted the 174 at the bottom with RG58.
Yeah, that's fine.
And the only thing I noted is that when I was doing the matching, I had to cut more off the tip to match the resonance.
Could be, but I don't. It depends on the length. You're getting down to resonance, anything can happen. But it should, if you find a good 50 ohm point here, it should be pretty consistent. Yeah, it should be independent of length, but that and as an antenna designer, I know it isn't, because if you have a slight mismatch, you're going to get nodes here, right, in the coax. So cut a few inches here and you'll find a better SWR. Add a few inches there, yeah, it will change slightly. That's why. But
Thank
yeah,
you, Dr. Fong.
theoretically, if it's perfectly matched. Any other questions? Okay, so I got it. What time is it? What time it is? Oh, 1 hour. Okay, we'll get it going. So here's our lab. Here we show these. And so my other talks are, we give one on how do you actually really get gain out of a JPole, not dual band, but like 5-6 dB gain. You do have to add elements. You got to make it into a collinear fashion. So I have a talk on that. And then of course we have a talk on our Triband. How do you actually get the thing going at 220 also on too? So that took us a while to figure out. And we don't sell radios, but we've tried these. And I have to say, I'm impressed with these Chinese radios. For $100, they're not bad. 2 meters, 220, 440, $100 or so for the mobile. The UV5R, they've got a ×3 one, which is gives you the 220. It works. We have them and we play with them. Okay, another thing we offer is about in 2012, I had a contract with CountyCom to build a software-defined radio, handheld. It uses the Silicon Labs chip. It covers, it's an HF radio, receive only, AM, single sideband. We have single sideband filters and demodulators with it. It also covers the low frequency band and FM stereo. This is for some government contract yet for emergency radios. Pretty good spec. I mean, it should last 225 hours on recharge or on a set of alkaline batteries. Really nice. I've got about 6 left. They gave us a bunch of these. If you guys want to order them, if you see them online from them, it's about $100 with tax and shipping. It's about 100. So if you're interested in one, I've got about 6 left. You get $35 off because they gave us a couple of cases of them. We didn't charge them for the design, and they thought, well, you want some radios? I said, sure. So I gave them to my students, and we've been people these seminars if you want them, but we are running on. We have about 6 left. That's it. So if you're interested, so here I'll give Wayne a spreadsheet, and you can mail it out, and you just fill in what you want, and then I just need a summary. The antennas, the one we just talked about, is $32. It comes in commercial too, commercial version, 152, 157, and then GMRS. FRS 460 to 470. So 2 versions, the ham version, commercial version. Same thing with the roll-up, ham version and a commercial version. And by the way, it includes a 6-feet extension. Of course, like I showed, all the adapters, so you don't need anything to buy. The Triband one I didn't talk about, but if you want it, it's $65, 2 meters, 220, 70 centimeters. It includes the PVC pipe. We have to ship it with the PVC pipe. And then extensions, 6 feet there, if you want them extra, $5. And an extra adapter, which is the BNC to PL259, 250. And of course, the radio I just mentioned, $65. But I'll send Wayne a spreadsheet you can distribute to you guys, and there's no rush. We're plenty busy. We with this antenna stuff, we've got a lot of good government contracts out here, surprisingly, because our antennas are pretty reliable. I would put them up against any commercial folks, and plus it goes to a pretty good cause. Okay, it is over 1 hour. So anyway, thanks a lot for your time on a Saturday morning. I'm amazed you guys get all these folks on a Saturday morning, and it's I guess lunchtime there. You guys can go have lunch, and I can go have breakfast. How's that? So you guys can email,
Thank you,
call
Ed.
me.
I definitely want one of your radios, Dr. Fong.
Yeah,